Hey folks, I hope you're hanging in there. We're on our second official full week of online learning and we're in chapter 21. Please go to Canvas and look at chapter 21 module and you'll see all of the things that you need to do there, including test corrections for exam 2. I'm offering 5 points, extra points for your exam, and the instructions are there. Also, please join us for our Zoom meetings every Tuesday and Thursday. 1:30 to 2:30 is the support, but anyone can join, and we do some really great problems there, as well as Tuesday, Thursday from 3 to 4. If I don't see your faces, I will be starting to send emails and checking in on you to see how you guys are doing. I miss you all, and I'm sorry that we're doing this virtual world here. But such are the circumstances. So hang in there, and then also be sure to answer in the discussion in chapter 21. There's a discussion group. You get 10 points if you answer some questions that I've posted for the Against All Odds statistics video with two means comparing, and also from this video. Okay, to make sure you're paying attention and watching. Thank you. Okay, so chapter 21 is all about comparing two means, whereas we're still using the T procedures as we did in chapter 20. Now we are using two X bars you'll be finding and two sample standard deviations, the S's. So with this, it's just a bigger formula, kind of similar to confidence intervals as we saw in chapter 20, and same with the significance tests as chapter 20, but with two X bars, like I said, and two standard deviations. So a two-sample problem can arise from a randomized comparative experiment that randomly divides subjects into two groups. Think about a treatment group and a control group in the medical world. It exposes each group to a different type of treatment, as we have seen in the past. Comparing random samples separately selected from two populations is also a two-sample problem. Unlike the matched pairs design studied earlier, there's no matching of the individuals. So we're not pairing up one individual from before, do a treatment, and then save the same individual. These are two different groups of people. The two samples, this is really important, are assumed to be independent, okay, so there's no connection, and they can be two different sizes. So you can have one sample size of 100 and another sample size of 50, and you can still compare the means of each of those samples. So the most common goal of inference is to compare the average or the typical responses in the two populations, and so that's where the X bar comes in. So the conditions for inference, just like we've seen before, two distinct populations, samples are independent. One sample doesn't have an influence on the other. They're completely independent of one another. We measure the same response variable for both samples. So we're looking at the same thing. Maybe it's a scores or outcome from a certain treatment. Both populations are normally distributed. The means and the standard deviations of the populations are unknown, like as before in chapter 20, but in practice it is enough that the distributions have similar shapes and that the data have no strong outliers. So that's kind of cool. So the first variable, it's going to be x sub 1 or x1, and x2 is the second variable. Sometimes though, for my subscripts, instead of 1 and 2, I might try writing x sub treatment and x sub control for the two groups, or x sub t and x sub c, so that I can differentiate them and it has a little more context for the situation. Here's how we describe the two populations. So we have population 1 right here, population 2, the variables x sub 1, but like I said, maybe it's x sub t for treatment and x sub c, and you can give it whatever name you want. If you do this, then for the mean it's mu sub t and mu sub c. Okay, standard deviations are sigma sub 1, sigma sub t, and sigma sub c. And you can see here we've got our sample standard deviation S sub 1 and S sub 2. To do inference about the difference, or to do inference about the difference mu 1 minus mu2 between the two means, we start from the difference between the two sample means, as we've said before. So moving on. Two sample t procedures to take variation into account. We'd love to standardize the observed difference, x1 minus x2, by subtracting its mean, mu1 minus mu2, and dividing the result by the standard deviation. The standard deviation of the difference in the sample mean is this lovely formula here. Because we don't know the population standard deviations, as in Chapter 20, we estimate them by the sample standard deviations from our two samples. So the result is the standard error, and here we go. It's standard error of the two differences in the populations is equal to this, using the sample standard deviations. Okay, so if you recall how we did it in Chapter 20, to standardize, we had our t statistic, and we did x bar minus the mean over s divided by the square root of n. Okay, I'm just showing this, taking a minute to show this because we have a new formula and it looks really scary, but it's not really scary, I promise. If you just follow all the rules of this, you'll be fine. So now, because we have two means, we have the mean, first mean, we're going to do the sample mean of the second one. You also need to find the two means, sample mean of the first one and of the second one, right here. You need to know your sample size. That's what we did before. Here's our sample size of the second one. And then in this case, this is the cool thing about these two means, is they often go to 0. Because in the case of inference, we're assuming that the means are equal, and we're actually looking to see if there is a difference. Just kind of like when we did matched pairs for this inference, where we did in Chapter 20. We did that H0 was, the mean was 0, like there was no difference in that matched pair. And now that the mean is something else, less than 0 or greater than 0, one of those. So this is definitely an option we'll be doing, and I'll show you this. Option 1 with software to use the statistic t with accurate critical values, but option 2 I'm also going to show you without software. So when you do this, the statistic t with the critical values from the t distribution, this is table C that we're talking about here. So table C, you take the smaller of your sample size, the smaller of n1 minus 1. These are your degrees of freedom, if you recall. So degrees of freedom, please note you take smaller sample size. Sorry, my pen seems to be going slowly. Smaller size. Okay, so moving on to the next one. So continuing on, this is for a confidence interval. Like I said, very similar to our last confidence interval. The only difference from Chapter 20 was that we had x bar, just one mean, plus or minus your critical t-value. So once again, you need to find your critical t-value with your degrees of freedom of the smaller sample. You take that size, sample size, and subtract 1, and that's what you're going to use in Table C. And then we did s divided by the square root of n. So the only difference, I want you to think about it, but do you see how the square root is just over all of this? Okay? So when you are testing a hypothesis, your H0 is going to be, instead, whereas we had the matched pairs where mu was equal to 0, you're going to assume that the two means are equal. The population means there's no difference between them. But what we often think is that there is a difference. Which one is the more effective treatment, for instance? So that's what you're going to have for your alternative hypothesis. So the different three possibilities of alternative hypothesis are, so the three alternatives, mu1 is not equal. Remember, this is 2 times your p-value, whatever you find in that table. You have to go down to the two-sided hypothesis, and you've got that one of the treatments is less than the other, less effective perhaps, or the first treatment is greater and more effective than the other treatment. Let's practice some exercises now. So I've included this in two modules, 21 and 20. So I would love it if you could record these, make a copy of this if possible, because this is going to be what we're going to use for the next 3 chapters. We have 20, 21, 22, and 23. As you can see, we've got these right here. So we've covered chapter 20. We use these formulas. Here's our confidence interval. Remember, you do confidence interval down here. It's one sample. We're looking at the mean. We go here to chapter 20, and this is our formula. This is the form from the calculator. You go to stat, and then you could scroll over to tests, and you're going to select number 8 for a t interval, and you'll be able to calculate the interval that way. Just so you know, I'm okay with you using your calculator from now on, except on an exam and in your practice, I do want you to set up this plug all the numbers into the formula so that I know that you understand which formula to use and where it's coming from. Okay? Same with the t statistic from chapter 20. So this was a test of significance. So we saw in chapter 20, one sample, we found the mean, chapter 20, and then here is our t statistic, and then we run our test of hypothesis test. So in stat test, then you go to number 2 and it's a t-test. So that's what you're going to use. I would add which calculator function to use for each of these as well, and you should just have the sheet with you all the time. It should just be for your viewing, because you're going to need all of these formulas. So today, if we are dealing with significance tests, you can see now that we're going to 2 samples. We're dealing with quantitative data still. We're dealing with means, okay? When we get into proportions, that's a part of the population. So that's a proportion. But right now we're still like testing, taking a bunch of samples, like a GRE score, and calculating the mean of that. That's measurable. That's what quantitative is. It's not a categorical, like I said before, the number of Republicans in California. That would be a proportion of the population. So then you go into chapter 21 right here, and you're going to use this formula. You can also say that in this formula that this right here, because we're assuming with our hypothesis test that the 2 means are equal, this is equal to 0. So really your formula is just this part. This always is 0, but it's nice to see it to understand where this formula is coming from. So that's the significance test. If you're dealing with the confidence interval, we're going to follow, it's a 2 sample now, so I'm going down this direction. It's a quantitative, once again, difference of means we're dealing with still. So we go this route, chapter 21. I take my 2 means, and this is my formula that I'm going to use. I'm going to plug it in, even if I use my calculator. This is a 2 sample t interval, and that is 0 on my calculator. If you scroll all the way down, you'll see the intervals are towards the bottom of the tests. And same, I didn't mention this one. This is the select 4, and it's a 2 sample t-test. Okay, and number 8 is the t interval for 1 mean. So t interval for 1 mean, 2 sample t interval for 2 means. And there are, if you want to go back to chapter 3, you can use the z-test as well, and that's chapter 17, and also a z-interval for chapter 16. Let me know if you can't find that, and I'll help you. This first example is a confidence interval with 2 means. Scores this year on the SAT mathematics test for students taking the test for the first time are believed to be normally distributed with a mean mu1, although we don't know that, remember. For students taking the test for the second time this year's scores are also believed to be normally distributed, so we want both of these things with a possibly different mean, mu2. These are both unknowns. We wish to estimate the difference, mu2 minus mu1, a random sample of SAT-M scores of 100 students. So here's our first sample. So we're going to say N sub 1, we have 100 students who took the test for the first time this year was obtained. And the mean of these 100 students, so we're going to say X sub 1 is 504.5 to that bar, while the standard deviation, S sub 1, is 100. a random sample of SAT-M scores of 30 students. So now we're doing another random sample, all the good words that we want to hear, who took the test for the second time this year was also obtained. Notice that our sample size is smaller, okay? But that's okay. We can still compare the two means. So x sub 2 is equal to 539.1, while the standard deviation was 90. Definitely an improvement, right? Just for future stuff, but you can kind of start to look at the means just from here. Given 95% confidence interval, mu2 minus mu1. Use the conservative value for the degrees of freedom. That means take the smaller sample. So in this case, we're going to take degrees of freedom. We're going to use the n equals 30, n sub 2. So my degrees of freedom for this, because that's the smaller sample size, is going to be 29. So 30 minus 1, 29. Now I want you all to go find the critical value in table C. So pause your video for a second and find table C, degrees of freedom are 29, and you're doing a 95% confidence interval. So look and see what that critical T value is for a second. It's really important that you do that. Okay, what do you all get? I hope you got 2.045. Yay! Now we get to plug all of these numbers into our big formula. Okay, so now we get to plug all these numbers into the formula. And like I said, at this point, if you want to use your calculator, as long as you plug them in, I'm okay with that. So we're going to take the means, the difference in the two means, which is going to be 500. I'm going to take the bigger one first. It doesn't matter necessarily, but I want a positive 504.5 plus or minus my critical T value, which is 2.045. And then you have a big square root. All of this stuff goes into the square root. You take your first, so I'm doing, since I'm doing my my 2 first, it's going to be 90 divided by my sample size of that one, 30 squared, and then we have plus, oops, it's not, made a mistake there, so that one's squared, the top, not the bottom. And then we have where's my other standard deviation? 100 squared divided by the sample size for that, 100. See how I lined up everything? I think that's really important. Put it all in a row or whatever cluster so that you can get them all lined up. All right, so we've got our formula laid out, and now we need to find out what this outcome is. All right, so when we're using our calculator, first thing, remember, you do have to plug in all of these numbers. So I want you to do all of the numbers, and then you can use the calculator to run the test. So we're going to do it's a confidence interval. So you have to scroll down to a 2 sample, not a Z interval, it's a T interval. So you'd hit 0. And then this is from stats. Notice if it was data, what comes up, you've got your list 1 and list 2. So that would be 2 data sets that you have, and you can enter them straight in right away into your stat and then edit your list. And then it'll calculate all of the means and the standard deviations for you. So that's really convenient. So now we're going to do a stat, and we're going to scroll down and we're going to enter in our data. So I did 539.1. I did for the first mean, I did the bigger one. And then 90, 30 for my sample standard deviation, and my sample size 504.5 for the second one, 100, and 100 for the standard deviation. You enter your confidence level. Don't worry about pooled. You can always say no, and you calculate. Drum rolls, please. Da, 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 da. And here is our confidence interval. It's right at the top. So we are 95% confident that the mean difference between students taking SAT, the SAT-M, the second versus the first time is between negative 3.992 and 73.192. So on the lower end of the difference, that just means that the other mean was greater than the first mean that we had considered to be our bigger one in general. So that's the difference. We have this range. All right, so let's move on to hypothesis testing. All right, so now we have a significance test. A researcher wished to compare the effect of two stepping heights, low and high, on the heart rate in a step aerobics workout. A collection of 50 adult volunteers was randomly divided into two groups, 25 subjects each. Group 1 did a standard step aerobics workout at low height. The mean heart rate at the end of the workout for this group was, so group 1, I'm going to use the L for the low step subscript, so we're going to do X sub L. The mean for that is 90 beats per minute, and then the standard deviation of the group with the lower step is 9 beats per minute. Maybe I'll even write that out so we don't forget about that. Our units. Group 2 is did the same workout but at a high step. So the mean heart rate for group 2, and we're going to do sub H for the high step. So that's 95.08, which is higher heartbeat per minute. And oops, I'm going to use H instead of subscript for 2. I just sometimes like to use the letters because then I don't forget what I'm talking about. The high step, the low step. Sounds like a jig. Okay, so assume that the two groups are independent. We like to know that, and that the data are approximately normal. That's good too. These, remember, this is going to represent the entire population of volunteers that contribute and do high step and low step. And then suppose the researcher had wished to test this hypothesis, so that our null hypothesis, I'm going to just write it down. Remember, always with these significance tests and two means, you set them equal. So I said that the mean of the low step heart rate beats per minute is the same as the high step. But the alternative is that actually the mean of the steps with the lower is going to be less than the mean with the high step, which is kind of what we were thinking. So now we're going to find our T statistic, and then we'll use our calculator. All right, so we're going to take our one sample T statistic to find it, and I'm going to say 95.08 minus my 90 divided by big square root. Standard deviation is 12 squared divided by both sample sizes are 25. And then for the second one we have, where is it? 9 squared divided by 25. And this is our T statistic. So this is what I want you to do when you're showing your work, and then we can calculate it, and that turns out to be, with the t-value of 1.69, I want you guys to pause for a moment, and I want you to look in table C now. Your degrees of freedom are 24, because our sample size for both of the means, our samples, was 25 this time. So we didn't have to take the smaller sample size. And I want you to go to that row, table 24, and I want you to sandwich this 1.69 and then go down to the bottom and look for the one-sided test. And I want you to find the two probabilities, or that P is in between. So take a moment, pause the video, and see if you can find that, please. All right, I hope you paused. Welcome back. So if you got that the p-value is between 0.05 and 0.10, you are correct. Technology actually gets even more accurate, so we're going to find that out now. Okay, so if you recall, you go to Stat, and you're going to scroll over to a test, and this is a two-sample, not a two-sample z-test. No, it's a two-sample t-test. So go here and then enter in your data from the stats. For the first one we had 95.08, and for standard deviation with that was 12. Next, sample size was 25, and then you had 90. I notice how I like to do the bigger one first. It's just easier for me. I find to keep that t-value positive, but it's not necessary. You'll still get the same outcome. You just have to remember when you're doing your null and alternative. Okay, so I think we set it all up. And in that case, since my subscript 1, I want that to be bigger, greater than mu2, if you recall, because mu1 was the higher step, so that's a higher heartbeat, so that's going to be greater than mu2. And if you guys get confused on which one to select, all you have to do is just try it. If you don't get the result you're looking for, then try the other one. Calculate and see how we got the same t statistic. So if you write your formula out and don't want to type this all into your calculator, put this all into your computer or your calculator and write down the 1.69. That's your t statistic. And then the degrees of freedom, you can see they calculated at different degrees of freedom. But our p-value is 0.0486 or 0.0487, we can say. So in conclusion, if we use table C, that would have put us with, because it's not as accurate, between 0.05 and 0.10 or 5 and 10%. This, using technology, knocked it down below the 5% level. So we can go with that's sufficient enough evidence that heartbeats per minute will be greater in volunteers with a higher step. So that's our conclusion, but if we were researchers, we might want to run a few more, take some more samples and just before we assume that. So that concludes our lesson for the week from me. Be sure to go to the discussion and answer the questions from these videos, and thanks for watching. I'll see you on Zoom. We'll go zooming. Ciao.